Institute of Aeronautical Engineering, Electrical and Electronics Engineering. Tech Talk. Name N. Venkat Sai. Roll number 23951802226. Branch and year. Electrical and Electronics Engineering, second year. Subject Digital Circuits. Topic Advanced Comparator Circuits. Advanced comparator circuits. In-depth exploration of comparator circuits and their applications. Introduction. This presentation develops into advanced comparator circuits covering their definitions, functions, and specific applications in various fields. We will also discuss operational amplifiers, comparators, hysteresis effects, and their roles in analog to digital converts. Introduction to comparators. Definition and function. Comparators are electronic devices that compare two voltages or currents and output a digital signals indicating which is large. Their fundamental process in circuit to serve as decision markers based on these comparisons, commonly used to trigger actions such as turning devices on off or generating outputs in a specific logical states. Types of comparators. These are several types of comparators, including open loop comparators, which have no feedback and can either be simple operational amplifiers or dedicated comparators. ICS. In construct, closed loop comparators utilize feedback mechanisms to stabilize output and minimize offset voltages, making them suitable for precious applications. Applications of comparators. Comparators find widespread use in various applications such as voltage level detections, zero crossing detections in AC signals, signal conditioning in sensor technologies, and as building blocks in more complex systems like phase lock loops and oscillators. Operational amplifier comparators. Configuration and circuit design. Operational amplifier comparators can be designed using standard op-amps in various configurations. Depending on the intended applications, designers may choose between inverting, non-inverting, or differential setups, paying careful attention to the supply voltages and input ranges to optimize performance. Voltage level and logic outputs. The output of an operational amplifier comparator is binary, typically transitioning between two distinct voltage levels corresponding to the input voltages comparison. Proper design ensures these levels align with required logic levels for interfacing with digital systems, which can include TTL or COMS standards. Advantages and limitations. Disadvantages of operational amplifier comparators including their versatility, availability, and ability to integrate into exciting analog circuits. However, limitations such as response time, output swing restrictions, and potential for oscillation in fast switching scenarios also need to be managed. Hysteresis and comparators. What is hysteresis? Hysteresis in comparators refers to the phenomenon where the output state depends not only on the current input levels but also on the past inputs. This result is in defending range hysteresis band of input values that prevent the output from oscillating between high and low states due to noise or minor fluctuations in the input signals, thus exchanging ability. What is hysteresis? Hysteresis is comparator refers to the phenomena where the output states depend not only on the current input levels but also on the past inputs. This results in a defined range hysteresis band of input values that prevent the output from oscillating between high and low states due to noise or mirror fluctuations in the input signals, thus exchanging stability. Implementing hysteresis in circuits. Implementing hysteresis can be achieved through positive feedback in comparator circuits. By adding a resistor from the output back to the non-inverting input, the feedback alerts the threshold voltage at which the comparators flip states. This configuration allows designers to set up specific threshold for switching economic variations in signal strength. Effects on signal integrity. Hysteresis improves signal integrity by reducing sensitivity to noise, which is particularly crucial in digital systems, where input signals may fluctuate around the threshold levels. This clear distinction between high and low states provided by hysteresis ensure that the output remains stable, preventing fails, triggering and ensuring reliable operations in noise environment. Comparator in ADCS. Roles of comparators in ADCS. In analog to digital converts, comparator serves a pivotal role by converting analog signals into digital representations. This compare the input analog voltages against the reference voltages and determine whether the output should be logical high or low, effectively enabling quantization or signal to be discrete levels. Role of comparators in analog to digital converts. In analog to digital converts, comparators serve a pivotal role by converting analog signals into digital representations. They compare the input analog voltage against a reference voltage and determine where the output should be a logical high or low, effective enabling quantization of signals to discrete levels. Sampling and quantization. This process of sampling involves capturing the analog signals amplitude at which distinct intervals. Comparators assist in determining the values of these samples against reference levels, leading to quantization, where continuous signals values are mapped to finite digital values, ensuring accurate representation of the original signals. Performance metrics. Key performance metrics for comparators in ADCS include speed or conversion time, resolution, number of bits resolved, input offset voltage and power consumptions. Each of these factors significantly impact the overall performance and efficiency of the ADC, and carefully consideration is required during the design phase to optimize these advanced comparator techniques. Low offset and high speed comparators. Low offset comparators are designed to minimize the input offset voltages, provided more accurate comparisons, which is crucial in precious applications. High speed comparators, on the other hand, are optimized for response time, crucial in high frequency applications such as signal processing and communication, ensuring rapid transition in output states. Comparator with integrated reference voltage. Comparators with integrated reference voltage source simplify the circuit design by eliminating the need of external reference components. This integration extends reliability and reduces the overall footprints of circuit, making them ideal of concept high performance designs. Design consideration for high precious. For high precious applications, factors such as temporary stability, power supply variations, and physical load play crucial roles. Designers must closely evaluate component selections, compensation techniques, and feedback mechanisms to maintain precious and ensure performance under varied operating conditions. Conclusion. In summary, advanced comparator circuit components in both analog and digital systems facilitating essential functions such as voltage comparisons, analog digital circuits operations, and exchanging signals integrity through techniques like hysteresis. Understanding their configurations, performance metrics, and advanced techniques is vital for designing efficient and reliable electronic system. Thank you.